Section 4.3, how derivatives affect the shape of a graph. First, we're going to visit what the derivative says about a particular function, and then we will visit what does the second derivative say about the original function. So for example, if I have a function like this, let me call this x1, let me call this one x2, let me call this one x3, and the last one x4. And this is a pre-calc question. I would ask you, on what intervals the function is increasing or decreasing. So we notice that the function is increasing on the intervals between x1 and x2. Okay, so it's increasing between x1 and x2. And then the other interval where it's increasing is between x3 and x4. And then you will say that it's decreasing on the interval between x2 and x3. Okay, and this is something very elementary. You can use your eyes to answer a question like this. But now, on the intervals where the function is increasing, what can you tell about the derivative? And the derivative, as you can see, at any point is a derivative that is positive. So, and we can say the same, similarly, we can say the same thing about this interval where the function is decreasing. The derivative is negative. So for decreasing, we have f prime is negative, and for increasing, we have f prime is positive. So this is summarized right here. If the derivative is positive on an interval, then f is increasing, and if the derivative is negative on an interval, then f is decreasing. And the idea is just to reinforce the fact that if we have a positive derivative, then that means that the rate of change is positive, and that means that the function is growing. Okay, the y values are getting larger and larger and larger every time, and that's all it's saying. In example 1, it says find where the function f is increasing and where it is decreasing. The idea is to find the intervals when the function is growing and when the function is not growing without having to graph. Okay, so we're gonna get our algebraic glasses on, and we're gonna be able to find what those intervals are. So the first thing you have to do is you have to find the derivative, because you wanna know what those critical values are in order to be able to tell if f prime is positive or negative. You wanna know when it is 0, and then before that value and after that value, we're gonna do a little bit of analysis. So first things first, let's just find the derivative. In here will be 12x cubed minus 12x squared minus 24x, and remember that derivative of a constant is 0. So now I want to make the derivative equal to 0. So to be able to do that, I notice that I have to factor first. There is a 12 that goes into every coefficient, and there is an x that I can factor out. So when I factor, f prime of x can be written as 12x times x minus 2 times x plus 1. And this comes from factoring out the 12x. And then what you have left is an x squared minus x minus 2. And then this factors into x minus 2, x plus 1. Two numbers that multiply them together gives you -2, and when you add them gives you -1. So now once it's factored, then it's easy to set up this equation equal to 0, and then each factor needs to be equal to 0 by the 0 product property. So if 12x equals 0, that means x is 0. So 0 is a critical value. If x minus 2 is 0, then 2 is a critical value. And if x plus 1 is 0, negative 1 is a critical value. So these three are our critical values. We don't know whether they are minimums or maximums. We will have to replace these values into f to see which one we're talking about. But we're not talking about finding minimums or minima or maxima. We're trying to find where the function is increasing or decreasing. So once you find those values, then you want to know what happens before negative 1. How does the derivative behave? Because you know that exactly at negative 1 the derivative is 0. It's 0 here, it's 0 here, and it's 0 here. So after you find the critical values, I'm going to construct some kind of a table that actually summarizes my findings. So before negative 1, you know, any number to the left of negative 1 is going to be less than negative 1. But if I have to write this as interval, it will be from negative infinity to negative 1. But I'm leaving this column in here, and you're gonna find out why I'm leaving this blank. But I need some kind of column to the left of negative 1. I need a blank column between negative 1 and 0, one between 0 and 2, and I need something to the right of 2 because I still want to know what happens after 2. I know 2 is a critical value, but in here the domain, since it is not specified, the domain is the domain of the polynomial, which is all real numbers. So I need to know what happens everywhere. Okay, so you know that f prime of negative 1 is 0, f prime of 0 is 0, f prime of 2 is 0. Okay. This one is I'm going to talk about what these two rows are for. Okay, so right now I'm going to work on the first one. I want to know to the left of negative 1 what is the sign of f prime. I'm not interested in finding out how much because I can pick a number, negative 2, negative 3, negative 4, but I don't care about how much is f prime at those points. What I want to know is what the sign is. So think of a small number that is close to negative 1, but to the left of it. So let's say negative 1.1. So negative 1.1 times 12 will be still negative. So I'm just going to put a negative sign. I want to keep track of how many negative signs I have multiplying. Negative 1.1 minus 2 will still be negative. And negative 1.1 plus 1 will still be negative. So when I multiply 3 negatives, the answer is still negative. So f prime is less than 0. Okay? Since I'm multiplying 3 negatives, my answer is going to be negative, so f prime is going to be 0. Now, between negative 1 and 0, what happens in between? So pick any number in the middle between negative 1 and 0, let's say negative 0.5. And now negative 0.5 times 12, I don't know how much that is. Well, I do know, it's negative 6, but it's going to be a negative number. Negative 0.5 minus 2 is still going to be negative. And negative 0.5 plus 1 is going to be positive. So I'm not evaluating negative 0.5, but I'm trying to find out what the sign of this will be. So negative times negative is positive, times positive is positive. So f prime will be bigger than 0. F prime is positive in between negative 1 and 0. At negative 1 is 0, at 0 is 0, but in between it behaves, it is positive. Now pick an x between 0 and 2, let's say 1. 12 times 1 is 12, is still positive. 1 minus 2 is negative, and 1 plus 1 is positive. So positive times positive, that gives me negative. So f prime is negative. And now to the right of 2, think of a number close to 2, but to the right of 2, I don't know, 2.1. This is positive. 2.1 minus 2 is positive. And 2 plus 1 is positive. So f prime is 0. Okay? So now let's see what you can tell about f. If the derivative is less than 0, f is decreasing. Okay, you can put a D if you want. D for decreasing. Now, between -1 and 0, the derivative is positive, so I know that it increases. Between 0 and 2, I know the derivative is negative, so that decreases. And then the derivative here is positive, so it increases. Since the question is asking me, find where this function is increasing and decreasing, I have to provide the intervals. So now I'm just going to provide the intervals. It is increasing on -1 to 0, and it's also increasing past 2. How do you write the interval past 2? Open at 2 and open at infinity. And then the decreasing intervals will be to the left of -1, but it is passing -1 to the left. So you say between -infinity to -1, and the other one that is decreasing between 0 and 2. You would leave your intervals open always, because you know that at -1 the derivative is 0, and here is 0 is 0. Okay, so these boxes are not to be filled, like that's nothing. So don't worry about those. I just want to know how it behaves everywhere else besides those points. I know at those points it's 0. So the graph here just confirms what we have said. Between -1 and 0, the graph is increasing, and past 2, the graph is increasing, and is decreasing before -1, and between 0 and 2. Notice how -1, 0, and 2, you have the derivatives worth 0, and then everywhere else the way we described. Now, this is the first derivative test, and this is widely used for the rest of the course. So please remember this and make sure that you do understand it. It says, suppose that C is a critical number on a continuous function. So for the function that we just visited, those critical values are -1, 0, and 2. It says, if f prime changes from positive to negative, then f has a local maximum. So in here, out of your table, you can figure that out. We're looking for a derivative that changed from positive to negative. This one is positive, negative. So before 0, it was positive. After 0, it was negative. So here, I know at 0, f has a local maximum. Okay, so I know x equals 0. We have a local maximum at x equals 0. You haven't found how much that local maximum is, but you know that it's happening at 0. If you want to know how much it is, then you have to do f of 0. Now let's keep reading. It says, if f prime changes from negative to positive, then you have a local minimum. So from negative to positive, in here the derivative was negative, in here was positive, so I know that 2 is a local minimum. So local minimum occurs at x equals 2. You don't know how much that is, you will have to do f of 2, but you know that it happens at 2. So let's see what kind of local is -1. It changes from negative to positive. So from negative to positive is also a local minimum. So not only x equals 2, but also x equals -1, you have another local minimum. And part C says, if f prime does not change sign at C, then f has no local minimum or maximum at C. And this is something that you can see, for example, if the function is x cubed, you know that it looks like a snake, and the derivative is 3x squared, so you know that the derivative is 0 when x is 0. So at 0, the derivative looks like that, and then you can see how the derivative is positive to the left of 0, and you know how the derivative is positive to the right of 0, so it never changes sign. That so that's why this is saying number 3 that if the derivative does not change sign, it doesn't, this is positive and this is still positive, then that point is neither local maximum or minimum. So this is a picture in here, and it's showing you that you can actually remember that by looking at that picture. But I want you to think about this. For example, let's say that you have something very positive happening in your life. Okay, so your derivative is positive. And then something happens, and now it's a negative situation that you have. So how are you? Very sad. Sad. Crying. You see your face? Okay. So now let's say that you have bad stuff happening to you, right? Bad stuff happening to you. Bad stuff means negative derivative, negative slope. And then something happens, and now you see positive stuff. So how's your face? Happy. You see? So when it changes from positive to negative, that's a sad face, so you have a local maximum. When your derivative is changing from negative to positive, you have a happy face, so you have a local minimum. Okay? And that way you can remember that. So this is the example that I have provided with x cubed. When the derivative doesn't change, this is positive, so it becomes positive, 0, positive, no maximum or minimum. And this is negative, so it goes from negative, 0, and negative. There is no maximum or minimum either. Now in example 3, it says find the local maximum and minimum values of this function having this closed interval. Now it doesn't imply that you have to find, the table of values that I showed you in analyzing whether f prime is positive or negative, but this is what you have to do every time you're finding local maximums and minimums. So it doesn't say to make a table, it doesn't say to use the first derivative test, but both things are implied in these kind of questions. So it is just going to become second nature whenever you do this, or whenever they ask you to sketch a graph of a function. So again, finding any kind of extrema, we need the derivative. When you take the derivative of this is what you're going to obtain, and then you want the derivative equal to 0. Now when I solve this, you know that the cosine of x equals -1/2, because -1 both sides and then over 2 on both sides. That's what you have. Since you are between 0 and 2 pi, then you can relate to the unit circle. This is 0, pi over 2, pi, 3 pi over 2, and then 3 pi over 2, and then 2 pi again. The cosine, remember that is for any point on the unit circle, the cosine is the x coordinate and the sine is the y coordinate. So if you want the cosine to be -1, this is where you are. So for what angles? Right here, the cosine is actually -1/2. So this angle right here would be 2 pi over 3. And then this other angle right here would have a third more than the pi right here. So that's why instead of, if this is pi, this is like 3 pi over 3 plus a third, 4 pi over 3. So you can relate to your unit circle if you want to do that. But these are answers that you will never be able to get on a calculator. And remember that you have to find the exact answer. So you can't use a calculator to do our cosine here. you have to know your values. So anyhow, the two values for x for which this is 0 is 2 pi over 3 and 4 pi over 3. So now I'm going to make a table. Now I know my critical values. Let's just put them in order. 2 pi over 3 is first, and then 4 pi over 3. And then since they give me a domain from 0 to 2 pi, then I want to include those 0 and 2 pi. I don't have to find things for those, but those are the ends. Okay, this is a super big table. You can just use as many rows as you want. So I have the derivative is g prime of x is 1 plus 2 cosine of x. Now I want to know between 0 and 2 pi over 3 what is the sign of this, if it's going to be positive or negative. So you can pick a number between 0 and 2 pi over 3. If I'm using my unit circle, let me pick pi over 2. Pi over 2, cosine of pi over 2 is 0, times 2 is 0, plus 1 is 1. So that is positive. Now, pick a number between 2 pi over 3 and 4 pi over 3. I can pick pi, and then I can evaluate it here. So cosine of pi is negative 1, times 2 is negative 2, plus 1 is going to be a negative value. And then between 4 pi over 3 and 2 pi, between this angle and this angle, I'm going to pick 3 pi over 2. And cosine of 3 pi over 2 is 0, times 2 is 0, plus 1 is 1, which is positive. Remember that I'm interested in finding out what is the sign of the function, of the derivative of the function, rather than finding out, evaluating values. So you know how it changes from positive to negative. So it changes from positive to negative. So you know that you're going to have a local maximum right here. And then it changes from negative to positive. So it changes from negative to positive. So you know that it curves like this, and you're going to have a local minimum there. So that's it. Then your answer will say local minimum at 4 pi over 3, and then local maximum at 2 pi over 3. Now remember that you are saying where it happens, x equals, but you're not saying how much they are. And since they are asking you to find them, then you have to do f of 4 pi over 3 and find out how much is that. In this case, it would be 4 pi over 3 plus 2 times the sine of 4 pi over 3. And then the local maximum would be f of 2 pi over 3. And that is 2 pi over 3 plus 2 sine of 2 pi over 3. Logically, you have to simplify this, find out how much the sine of that is. I think is rad 3 over 2, so it would be 4 pi over 3 plus 2 rad 3 over 2. And in here will be 2 pi over 3 plus 2, well, this one will be negative rad 3 over 2, this one will be positive rad 3 over 2. So you have to remember what the unit circle is. And now in here on this picture is showing you what we just said, the local maximum at 2 pi over 3 and the local minimum at that 4 pi over 3.